A very good day to Dr. Sukri. I'm Zichi from Group Meta. Today I'm going to present about my group safety simulations battery pack cooling project. Let me introduce my group member. For the first one is Chong Jingro, and the second is me, Zichi, and Ding Hui Kian. Here comes to our first part, introductions. There are various types of car batteries such as lithium-ion, nickel metal, lead acids, and ultra-capacitor. Among all these battery types, lithium-ion battery pack is one of the most applicable options and extensively used battery pack for electrical vehicle. Air-cooled is the most commonly used technologies in battery pack cooling due to its cost and is the simplest compared to other cooling method. The cooling performance of this method is strongly related to the airflow in the system as well as the inlet and outlet of the system, cell arrangement and space between each cell. We will be studying the streamline on how the airflow within the battery with our design dimensions and the relationship between air velocity and the desired temperature.
So for the next part is the methodology. For the geometrical model, a battery pack consists of 32 pieces of lithium-ion battery cells with an electric configuration of 8 cells in series and 4 cells in parallel was developed for the current study. The battery pack dimension is 174 mm x 88 mm x 71 mm. The inlet and outlet were designed to be positioned on the center part of the front wall and the back wall respectively. The material property of the air and the aluminum is set as shown in the figure. For the element type, the tetrahedron mesh was applied. And for the boundary condition, the inlet temperature was set to 23 degrees Celsius and an average heat generation rate of 2.75 watt were used at the thermal boundary condition at the cells. The real number is 1.6 times 10 to the power of 5 and the inlet free spring velocity is 1.5 meter per second. The inlet and outlet domain were given velocity inlet and pressure outlet boundary condition respectively. The flow heat transfer coefficient is set to 500 watt per meter square Kelvin. For the solver setting, pressure, base, and absolute velocity formulation have been chosen. Based on the real number, turbulent force is applied. For viscous model, the K excellent model is chosen. The discretization method is set as shown in the figure. The conversion criteria will set to 0.001 in the residual setting.
For the following present was about the mesh sensitivity analysis. 4 different grids are evaluated for mesh sensitivities analysis to determine the battery temperatures. As shown in this figure, started from the second mesh, it shows small deviations as compared with the third and fourth mesh. So second mesh is being chosen for the entire project simulation.
Hi, my name is Chong Jino from Meta Group. I'm going to present the result and discussion part. In the result and discussion part, we have 3D streamline, temperature, velocity, and pressure control, graph of temperature against length of housing, and comparison between average temperature and uniformity temperature versus velocity. As shown in figure 1, the streamline is spread evenly after the air enters the inlet of the battery pack. There are more yellowish color streamlines at the inlet of the battery pack compared to the outlet, so we can observe that the streamlines show less obvious at the gap for each of the battery cells. As shown in figure 2 and 3, temperature distribution control from the inlet with the velocity of 1.5 meter per second ensure that the temperature of the battery cells rises as air is being flowed through every cell along the housing. The battery cells that located in the middle for the last 2 rows are assumed to have no experience any cooling by the airflow. Next, for the velocity control, as shown in figure 4, the airflow velocity between battery cells decreases to a minimum velocity right after passing through the front row of battery cells, leading to an increase in the maximum temperature and a loss in temperature uniformity. And the next one is the pressure control, as shown in figure 5. The inlet of the battery pack had experienced the maximum pressure due to a sudden high velocity airflow being forced entering the battery pack from the inlet of 200 mm square. From the figure 6, which is the graph of temperature against the length of housing, we can clearly observe that the temperature along the 3 lines of the housing increases as the length of the housing increases for about 0.155 meter, but the temperature shows a slightly drop after the length of 0.155 meter. Although with that, the final temperature at the end of each line for the housing are still a high temperature than inlet. The last part of the result and discussion is the comparison between average temperature and uniformity temperature versus velocity. Figure 7 shows the graph of average temperature versus velocity, while the figure 8 shows the graph of uniformity temperature versus velocity. Based on the figure 7, the average temperature decreases as the inlet velocity increases, while based on the figure 8, the uniformity temperature also decreases as the inlet velocity increases. Therefore, the graph of average and uniformity temperature against velocity are also shown in similar pattern.
And for the last part of our presentation is our conclusions. For our design model geometry of battery pack can achieve the optimal operating temperature of lithium-ion battery, which is between 25 degrees Celsius and 40 degrees Celsius, and the desirable temperature uniformity and also successfully to obtain at the range which less than 5 degrees Celsius. Our design of battery pack can still be improved due to the velocity and pressure are decreasing to a minimum after passing through the front row of battery cells. This result shows the lower pressure and lower velocity at the outlet might cause some hot air still trapped inside the battery pack. Therefore, the gap between the battery cell can be larger to let more air flow to each of the battery cell to enhance the thermal performance of the system.